Hello everyone and welcome for another Mountz webinar. Today we are going to review 5 error-proofing techniques that will help improve the quality in your assembly processes. So before we jump to that, a few words about Mountz. Mountz is a family-owned company that was created in 1965. Our headquarters are in the Silicon Valley, Northern California. We also have a warehouse and laboratory in Alabama, which is also a service center. And we recently opened an office just a few miles away from London for sales and service. Mountz, since its creation, has always been a company that was 100% focused on torque. As such, we were the first company to manufacture an electronic torque analyzer for a very famous defense company in the early 70s. Of course, on top of torque measurement equipments, we also have tools to apply torque, such as hand tools, electric, and air tools. Our customers operate in very various fields of operations. Some of the main ones are medical, defense, aerospace, automotive, and electronics. But basically, we have customers in every field. Wherever there is a screw, there is a tool that needs to be used to fasten the screw. As of myself, I'm Adrienne, a technical sales manager within the international team. I have more than 12 years experience in the assembly business, so I've faced a lot of different applications, a lot of different problematics, and I have experience bringing solutions to our customers, including error-proofing solutions. So when we talk about error-proofing, there is a term that you most probably have heard of, which is a Japanese term, pokayoke. This literally translates in mistake proofing. This mistake proofing is really around us in our everyday life, and we don't really pay attention to that anymore. As an example, when you have an automatic car and you want to start it, the gear needs to be set on park or neutral. When you get into an elevator, there are sensors that will prevent the doors from closing in on you and prevent the elevator to move at the same time. When you fill in the gas to your car, the nozzle will stop delivering gas when the tank is full, really preventing any overflowing. So error-proofing is all around us in our everyday life. Now, before we keep on moving on, I want to ask you a question, and you can answer in the chat. Yes or no, or you're not sure. Do you currently use any error-proofing tools in your assembly process? Let's give you 30 seconds and gather the results. So I see that nobody is using error-proofing systems. Some of you are selling them. So it is great that we are here today because we'll be able to highlight those for you, for those of you who sell this type of tools, but also for those of you who use assembly tools. So error proofing is, of course, directly linked to manufacturing risks. What are those risks? Well, in the assembly, there are several types of manufacturing issues. When a part is not properly assembled, it can go out to your customers, and this will result in customer returns. So the part is returned from your customer back to you because it's not properly done. So this will have a direct financial impact, of course, but it also have an impact on the productivity, because whether the part comes back from your customers or an error is happening on the line, it will impact productivity as the parts need to be reworked. So while the operators rework on the parts, they are not assembling new parts. These customer returns will also be linked, of course, to the company image, which can be deteriorated because of this, and will also be linked to later on marketing issues. But the most critical risks that you and your customer runs are liability. Now let's imagine that a part goes out on the field and is at the heart of an accident happening, and that later on, through the investigation, the part is found to be faulty due to a wrong assembly process or a wrong event during the assembly process. So in this case, the company, you or your customers, can be found liable and responsible for this accident. And of course, this will have a big impact on your company, financially, productivity, but also judicially and in terms of image. There are several sources for these manufacturing issues, and the first one can be linked to the human factor. So we have, and you have, operators working on the assembly stations every day. And of course, everybody is human. So the operator may misunderstand the process. They may lack experience or training to properly deliver the assembly on this specific part. They can be interrupted through breaks or through other events around them. This can be directly linked to forgetfulness, where parts or fasteners are forgotten on the part. The operators may also misidentify parts, and all of these may also be linked to the lack of supervision. So this is for the human factors. When we have a look at other causes, they can be more linked to the process itself. Procedures may not be followed properly. There may be some errors in the assembly process, missing parts, incorrect tightening, the wrong torque, or the fastener not being fastened properly, but also the improper tool being used on the fastening. So the operator uses a wrong tool for the wrong application. As we focus here on the assembly, there are many common tightening failures. The first and most common one is going to be the fastening control. So you want the torque to be delivered, the target torque to be delivered, and you want, of course, the fastener to be properly fastened. This is not always the case. The torque may not be delivered properly. This can be due to cross threading events or the fastener not going all the way down, some parts missing on the assembly. Also, once again, the improper tool being used, missing fasteners, and of course, the tool performance itself. Fastening tools may not always perform as you would expect them to do. So when we talk about error proofing, there are 3 levels of aim that we are looking for. The first level will be to detect the errors, allowing you to immediately notice that something went wrong in the assembly. The second level will be to minimize the errors happening, and the optimum level will be to totally eliminate any assembly issues happening on the workstations and on the line. These can be done through different ways. It can be done, as an example, by replacing the current tool you have by a tool that will allow you to do so through different features that we will see throughout the course of this webinar. It can also be done through a more automated process, whether it's a full automation process through robots or semi-automation where the tools, the operators, and the workstations will work in symbiosis to deliver the proper quality that you are looking for. So today's webinar is focusing on 5 techniques for error proofing. So what are those 5 techniques that we will see? Well, the first one is really to have a good fastening control, making sure that the torque is reached properly. The second is also to have a process control, which is where we are going towards semi-automation. Third technique will be to use screw counting features, making sure that all the screws are fastened on the parts when they leave the station. There are also tools to guide the operators that we will see right now. And finally, the 5th technique will be done through monitoring in real time, but also for traceability. So the first technique is really fastening control. So what does that mean? Well, when you have a fastener and an assembly process, you have a target torque and a torque tolerance. So you need a tool that will allow you to set this target torque and this torque tolerance. But on top of that, you want also a tool that will allow you to set the speed you are looking for, whether it's for increased productivity or to respect the integrity of the part, especially when you have, as an example, plastic applications. You want to find the right setting for your application. But we have talked about cross-threading as an example. And in that case, the target torque can be achieved within the tolerance. It doesn't necessarily mean that the fastener was properly tightened. So this is where the fastening control will also include angle windows to ensure that the target torque was reached and that the fastener went all the way down exactly as it's supposed to. There are also ways to prevent the operators from stopping the fastening while it's happening. And of course, any event happening out of your target, torque tolerance, angle window will result in an error being detected. So it means that you will be able to notice that on spot and take actions immediately. So fastening control is the first technique. Second technique is process control. So fastening can be the fastening control. We can call them presets. And the process control will allow you to combine those presets together to really have a semi-automation approach to the fastening, where the tools will communicate with the workstation, PLC network, and really reduce the operator's influence by allowing the different presets to go step by step, automatically guided by the tool. What that means also is that as you can combine presets together, you can reduce the number of tools that are being used on the workstation. You can even decrease the number of workstations on the line. And of course, this will be directly linked to lesser issues and to improve quality assembly. The third technique that we talked about is screw counting. So screw counting, the main aim, obviously, is to ensure that all the right amount of screw has been done properly when the part leaves the workstation. You want to make sure that this is done, and this can be done through different process, automatically, with time control, or through once more real communication between the tools and your workstations. The fourth technique we talked about is operator guidance, which can also be called a job manager. So the operator guidance will help the operators know where they are at on the assembly process. It can help train them, and it can be really a substitute for the lack of training and the lack of experience through a complete visual guide that will really be a very strong support for your operators. When we talk about error proofing, we talk about monitoring. Monitoring is going to be at the center here to detect errors, visually indicate them on the tools, communicate them through the IOs on the tools with stack lights or to PLCs. And it's also going to allow you to get those data in real time to your network for once more identifying if anything goes wrong in real time, but also keep track of this data for full traceability. Traceability is a keyword now in the assembly, and this is something that is really important in many fields in the assembly business. So now that we've talked about the theory, the different aspects of error proofing techniques, let's go on with the demo. To do the demo for this webinar, I'm going to get the support of some tools. I'm going to use the ECT series, which are transistorized cable tools. And I'm also going to use the EPT series, that are battery transistorized tools. So let's start. And if at any point you have any questions, feel free to write them in the chat. We will review those questions at the end of the webinar and make sure that we answer them for you. So let's go ahead. The first technique we mentioned about is fastening control. So you want a tool that will allow you to set your target torque. So here, when we look at this controller, the ECTD controller. It's easily done through the touch front panel. We enter through the password, and then we have 4 different submenus. Going to the fastening process or the fastening settings, we have here 2 main strategies, which are TCAM, torque control angle monitoring, or ACTM, which stands for angle control torque monitoring. So what that means is that you either have a target torque with an angle window or a target angle with a torque window. Let's move back to target torque and angle window. Second line here is target torque. We can easily change this target torque here using the arrows or touch on the field and enter any value within the range of the tool that's connected now to the controller. So we can set 3 Newton meters, and now our target torque is set for 3 Newton meters. The third line just beneath the target torque, as you can see, is torque limit in percentage. So this is where you can set your torque tolerance. So is in this example 10%. So with our target torque of 3 Newton meters, we will know that the tool, anytime the fastening is declared good, will have been applying the torque between 2.7 and 3.3 Newton meters. With these tools, this is directly linked to the built-in transducer that is surveilling in real time and at all time the torque being applied by the tool. So you know that when the tool tells you that it reached 3 Newton meters, this comes from an actual torque sensor built in the tool, and that the tool really reached 3 Newton meters. The third level here is going to set angle requirements to avoid cross-thread or to avoid missing parts. And this is done through those settings here, where just like for the other parameters, we can simply touch, enter the value for the minimum angle, 300 degrees, enter the value for the maximum angle, 1080 degrees. So now we will know that the torque is reached, 3 Newton meters, and it was reached within this angle window. And the fourth step, this fastening control, is going to prevent the operator from releasing the trigger. So what we can see is we have 2 ways to achieve that. When we look at the controller menu, we have here a fastening stop error. And when we enable this parameter from off to on, anytime the operator releases the trigger before reaching the target torque, we will have an error signal. But another way to achieve this is through the trigger start, which means that once activated, even if the operator releases the trigger, the tool will keep on working until either the target torque is reached or the maximum angle is reached as well. So it's really a way to prevent and eliminate operator influence for this assembly. So I will deactivate this one, but keep activated the fastening stop error. When we come back to the main screen, we have some information here available. We have a target torque, 3 Newton meters, and a target speed, 150 Newton meters, 150 RPM, obviously. This speed can be set automatically through the tool, or you can set it yourself depending on your needs. So let's see what happens now when we make a fastening. So we have a screw plate here, and we can make fastening. Fastening, okay. Our target torque is 3 Newton meters. We reach 3 Newton meters. We have the OK signal. If we move to the next screw, same happens. 3.01 Newton meter was reached. Everything is okay. Now let's simulate a cross threading by fastening an already tightened screw. Here, in this case, we reached 3 Newton meters, but we reached it before the minimum angle, so we had an error signal. We can also do the same, simulating missing parts, which will result in the fastening taking too long, so the screw turning more than it should. And in this case here, we reach the maximum angle, so the tool stops, and the error signal is sent on the screen, easily noticeable for the operators. What happens also is if we start the fastening but release the trigger, we have an error signal once more telling us that no torque was achieved and something went wrong in the assembly. So as you can see, really a wide array of solutions to indicate us when something goes wrong in the assembly, but also when everything is okay during the fastening. So this is related to fastening control. Now, there are also ways to implement process control, and this can be done through different presets. So when we come back to the preset window, fastening, you can notice at the bottom here that we are 1 out of 15. So that means that there are 15 presets available on the tool, and I can easily go to any of them, and for each of them, set a specific target torque or target angle with the torque tolerance, the speed, the angle, just as we've just demonstrated. And on top of that, we can also use these presets and combine them together. So this is done through what's called model, and this is here. Just like for the presets, we have 15 models available. In this case here, we are using the model number 1, and for each model, we have 20 different lines of commands. So what is a line of commands in a model? Well, a line of command can be several steps. It can be a fastening step. It can be a delay between the previous and the next step. It can be an input step where an input signal needs to be received on a specific pin before moving to the next step, sending an output signal when the previous step was done properly, or also a barcode reading event where, just like for the input, we will be waiting for a specific barcode to be read before we move to the next step. So when we select fastening, and this is what's done here in this example, we can combine presets together. So we can use the step 1 with the preset number 1 and the step 2 with the preset number 3. So whenever this line is done, the tool will automatically move to the next step, and so on and so on. But what you notice also here on the screen is on the right column, we have a count. So we can count, we can indicate that we want to make the first step with preset number 1 for 3 screws. We can do the same for the step 2 using preset number 3 for 3 screws as well. Now that we've programmed our model, we need to activate them in the controller section. And we have here the model selection mode that we will activate. And then you will see that the front screen has slightly changed. Where we used to have preset 1 here, now it's indicating us that we are using model number 1, using preset 1 for the step 1, which is a fastening step. So let's see how the tool navigates between the steps as we go on. So now that we've done our 3 screws using preset 1, we move to the step number 2 using preset 3. Here, there is something I want to attract your attention to, and it's this little window on the bottom left, which is the counting window. And as I make the fastening, you will see that the information here changes. And now, out of our 3 screws for the step number 2, we have 1 remaining screw. And once we've done it correctly, the cycle complete is sent, and we can buckle back, loop back to the first step using preset 1 for fastening for 3 screws. So screw counting is important. We can, as we've just seen, use the models to this effect, but we can also use screw counting as a more global setting. So to do that, we need to deactivate the models. So I'm going back to the controller window and back to using the presets. And you will see here that we have a screw count menu. So we can set here the total number of screws that we are aiming for, 3, 5, 10, etc. We can then set a middle count number, which can be used for subassembly works, where we need to receive the signal after a certain number of screws is done before we can move on to the next and total number of screws. But here, there are different ways to manage the screw counting. We can do it automatically, and as soon as the screw is done properly, the controller will count it. But we can also set it in a more communicative way with the workstation, where we can have a continuous on signal sent on a specific pin so that we are counting. If the total number of screws is not done before the signal goes down, we will have an error signal. We can manage a pulse as a starting point for the counting and set a time limit. In this case, again, the screws all need to be fastened before the time limit is reached. In other case, we would have an error signal, or we can have a pulse signal for the start and also for the finishing point of the counting signal and the counting program. So let's count 3 screws here and come back to the main screen. Now, on the bottom left, you see that we have 3 screws remaining out of 3, and I can use any of the presets to make this counting program. So let's make the first one with preset number 8, target torque 5 Newton meters. Now we have 2 screws out of 3 remaining. I can change my preset. It can be done through the I/O as well. And let's go back to preset 1. And here, let's make a mistake. Once again, cross-thread events. The screw was not properly fastened. And of course, you will notice that here, this wrong fastening was not counted, as only proper fastenings are being counted. So we can move on. We have now done our 3 screws. We look back to 3 out of 3. And once those 3 screws are done, we have the signal sent. So this is related to screw counting. Now there is another way to manage the screw counting, but also to really be a guidance for the operator. And this is through a job manager. So the job manager, to demonstrate this feature, I'm going to use the battery tools. So this is here the controller that's connected in Wi-Fi to the battery tools. We have 2 tools connected now to the controller. And when we talk about job manager, we really talk about, once more, a real support for the operators. So how is it done? We click here, job manager, and in this case, we have one job that's created, that's a demo job. We can click on edit, and then we have different steps, different commands that can be done for each line of this job manager. We can use the steps as a fastening, input, output, delay, or display a message. Very similar to what we had with the models on the Cordy tools. So what I'm going to do here is first display a message to the operator to use the pistol tool. I will display this message for 5 seconds. And once those 5 seconds are done, we can move to the fastening step. And this is where we can select the tool needed to be used for this fastening step. We can also set how many screws we want to be done and which preset to use for these 2 screws in this case. So still very similar to the model. But here we have another feature, which is, as you can see, the picture of the part. So going here, we can easily set which are the positions for each fastening and display those to the operator. In this case here, we are waiting for the allocation of the position for fastening number 1. And when you want to change it, that's very easy. You just point on the screen to where you want this position to be set. If it's on the right side, you simply move the menu to the left and again pinpoint to where you want this fastening to be happening. If you want to have the full picture, you pull down the menu and once again just point where you want. So let's set it back here. Of course, each part is going to be unique, so we can, for each position, increase or decrease the radius of the position. We can also increase or decrease the radius, the width, sorry, of the line for the position. We can change the color. Here it's yellow. We can change it to Mountz orange as an example. And this is going to only affect each position individually. Once we are done with position 1, we can move to position 2 here and do exactly the same for it. So, okay. Once those 2 positions are done properly, we move to the next step, which is display this picture using a head tool to the operator for 5 seconds. And then same story here with the picture where we indicate the operator where are the positions to be done with this angle head tool. We save this job. Okay. Let's go back home now and start our operation. Here we can select the job that's being used. We start it. We display the use pistol tool for 5 seconds. And now we indicate to the operator where is the first fastening position. So this can be displayed on the controller itself, but the controller also is equipped with an HDMI port so that this display can be relocated to another screen on the workstation that may be more accessible for the operator, or a wider screen for several operators to review the job at the same time. So the trick here is really, again, to error-proof, which is the subject of the webinar today. So what that means is that only the pistol grip tool is going to be working for these 2 first positions. If the operator tries to take any other tool, these tools will not be operating, so the operator will not be able to use the wrong tool for the wrong application. So using the pistol tool, I'm going to make the first fastening okay, second fastening okay. We display to use the angle head tool. Now the pistol tool is disabled. I need to take the angle head tool to make the fastening. Fastening okay. Fastening okay. The job is okay. And we look back to the first step. Then we can also simulate when something goes wrong during this process. So 2 first fastening are okay. And here I'm going to have an error. We have an error signal here. This position was not done properly. And in this case, we have several ways to manage. We can either stop the process and start with a new part. We can skip this screw, or we can retighten it for a specific number of time before we move to the next position. So in this case, I'm going to skip it. Go back to the full screen view. And in the end, even though the fourth screw fastener was properly done, we have a job not okay signal as the screw number 3 was not done properly. So it's really, once again, oriented towards training, visual guidance, but also error proofing your assembly process. So now going back to the Cordy tool, we can see real-time monitoring. So real-time monitoring will take several different shapes. It will be done through the data being sent through the I/O. So the battery tools, controller, and the cable controllers are equipped with input-output. So here we can monitor them, but we can also assign them exactly the way we want through different steps. So we can set any of these commands to any of the input pin. Similarly, on the output signals, we can also assign them exactly the way we want. And what you will see here are the most commonly used ones: fastening OK, count complete, so that all the screws were done, but also alarm signal here, something went wrong during the assembly. So these are available through the I/O. But we can also use, so we've seen the setting of the I/Os, but we can also use the network capabilities of the tool. And each of the tools here will communicate through the RS-232 or Ethernet ports, and will be sending data in real time to the assembly, to the network, so that you collect all the fastening data, target torque, torque achieved, date and time, speed, if something went wrong, what went wrong, counting. So every feature that we've just talked about is available through the real-time monitoring, through the RS-232 and Ethernet ports. We also have the possibility to display a graph, whether it's with a corded or with a battery tool. We can have torque and speed as an example. And if we start here, we have our speed in orange, the torque in blue, and this is going to help us see what's happening in the tool in real time. And of course, the graphs can also be collected through the network ports. So now we are reaching the end of this webinar. If you have any questions, feel free to write them now in the chat. If you are watching this video on demand, feel free to write to us at international@mountztalk.com. We will be happy to answer those questions. Tom, do we have any questions?
Hey, Adrienne, so we've got a couple of questions here. First one is, what is the difference between transducerized and non-transducerized tools?
Okay, that's a very good question. A lot of customers in the industry are not aware of the advantages of having transducerized tools and the difference between indeed a current control and a transducerized tool. So a transducerized tool means that basically there is a built-in torque sensor in the tool, and this built-in sensor is reading in real time the torque being applied and being delivered by the tool. So it's really what's called a closed loop with a full communication between the electric motor, the servo motor actually, the sensor and the controller, making sure that the tool stops when the target torque is reached. For a current control tool, the way of working is a bit different. Here, the main difference will be that there is no sensor, obviously, so that the communication happens between the servo motor and the controller. And in that case, the torque delivered by the tool is calculated through an algorithm in the controller, ensuring that the tool, once again, stops when the target torque is reached.
Okay, and the next question is, I don't have a network, but I still need to record and store data. Am I able to do this?
Yes, you can do that. On the tools that we've seen today, whether it's the battery tools or the cable tools, there are some data storage features. So first, each of the controllers come with an SD card so that the data is recorded as a CSV file. So it's an Excel file that you can easily use later on for traceability. And when we talk about the battery tools will themselves record 3,800 points of fastening data and back this fastening data to the network as soon as the Wi-Fi connection is established once again.
Okay, and that's all the questions, Adrienne.
Okay. Well, we want to thank you very much, everyone, for joining us today for this webinar. If you have any questions, feel free to reach to us again, and we are looking to welcome you again next time. Thank you. Bye-bye.